Every single second of every day, there's a silent, microscopic war being waged inside your body. It's this constant battle against viruses, bacteria, and just countless other invaders. And the force that's defending you? Well, that's your immune system. And it's a defense network so complex, so intelligent, it honestly rivals any army in human history.
So let's get right into it. We're not just talking about the general grunts here. We are talking about the body's special forces. These are the highly trained specialized units that learn, adapt, and remember every single enemy they face. This is your adaptive immune system, and we're about to meet its key players.
Okay, so how does this elite army actually operate? To really get a grip on its role, we first need to kind of zoom out and see the bigger picture. See, our body has two main lines of defense, and they work together. Let's break them down.
On one side, you've got the innate immune system. Think of these guys as the general guards. They're super fast, they're always on patrol, and they attack anything that looks even a little bit suspicious. They're your first responders, for sure. But on the other side, you have the adaptive immune system. And these are the elite specialists. They're a little slower to get going at first, but their attack is incredibly specific, unbelievably powerful, and, this is the most important part, they never ever forget an enemy.
This diagram here gives us a fantastic overview of the whole command structure. Over on the right, you can see the innate system with its generalist cells. But our focus today is on the left side, the adaptive system. And it's broken down into two core divisions. You've got cell-mediated immunity, which is led by T cells, and antibody-mediated immunity, run by B cells. These are the two main special forces units we're going to get to know.
Right, so before any army can actually fight, it has to know who the enemy is. So what exactly is the red flag? What is it that mobilizes these elite T and B cells?
Well, the trigger is something called an antigen. An antigen is basically any molecule. It's usually on the surface of a pathogen, like a virus or a bacterium, that our body recognizes as foreign. The best way to think of it is like the enemy's uniform. It's the signal that just screams, "I don't belong here."
But what's really fascinating is that our immune system is even more precise than that. It doesn't just see the whole uniform, it recognizes specific little parts of it. It's kind of like the rank insignia on a shoulder. As you can see in the diagram, these specific binding sites are called epitopes. And, sometimes a molecule is just too small to be seen as a threat on its own. Think of it as just a single button, not a whole uniform. These little guys are called haptens. But if a hapten attaches to one of our own proteins, that whole package suddenly looks foreign, and that can trigger a full-blown immune response.
So, the enemy has been spotted. We can see its uniform, its insignia, but how is that information passed up the chain of command to our special forces? Well, that requires a dedicated intelligence network.
So, meet the scouts of the immune system, the antigen-presenting cells, or APCs for short. Specialized cells like these dendritic cells and macrophages are constantly patrolling our tissues, and when they find an invader, they literally swallow it, break it down, and then they present a piece of its uniform, the antigen, right on their own surface. They're basically carrying the enemy's flag back to headquarters to show the T cells exactly what to look for.
And they don't just hold it up. They present this evidence on a very special platform called the Major Histocompatibility Complex, or MHC. Think of the MHC as a molecular bulletin board. And there are two main types. MHC class 1, over on the left, is used by almost any cell in your body to basically scream, "Help, I've been infected on the inside." It's an internal alarm. MHC class 2, on the right, is used by our APCs to announce, "Hey, I found an enemy floating around outside." And this distinction is absolutely crucial for deciding which type of special forces to send into battle.
All right, so the alarm has been sounded. Now it's time to meet the first branch of our adaptive army that responds to that alarm, the T cells. You can think of them as the ground forces, the commanders and the assassins of the immune world. Now, T cells don't just roll off an assembly line ready to go. No, they go through an incredibly rigorous training program in an organ called the thymus. It's basically boot camp. In there, they go through positive selection to make sure they can even recognize the MHC bulletin boards, and then negative selection to get rid of any cadets that might accidentally attack our own body's cells. Only the absolute best and safest soldiers graduate.
So once they're activated, some T cells become T helper cells, and these guys are the field commanders. They're coordinating the entire battle. They don't fight directly, but they are given all the orders. This table really breaks it down. Th1 cells rally the macrophages, our heavy infantry. Th cells call in the B cells, which, as we'll see, are kind of like the Air Force. Th17 cells are the recruiters, bringing in more frontline soldiers.
And then, so importantly, you have Treg cells. They act like the military police, telling everyone to stand down once the battle is won to prevent friendly fire.
And then you have the assassins, the cytotoxic T cells. When one of our own cells raises that MHC class 1 alarm flag, the one that says, I'm infected, these guys are dispatched. They lock on, release a protein called perforin that literally punches holes in the compromised cell, and then they trigger a self-destruct sequence called apoptosis. It's a clean, surgical strike to eliminate an internal threat.
Okay, on to the second major branch of our adaptive army. While T cells are the masters of that close-quarters combat, B cells are in charge of long-range warfare. They run a very sophisticated weapons factory.
So when a B cell gets the signal, and it often comes from one of those T helper cells, it goes through this incredible transformation. It becomes a plasma cell, which is essentially a single-purpose factory just dedicated to churning out millions upon millions of these tiny, Y-shaped protein weapons called antibodies.
Let's just take a second to appreciate the brilliant design of these things. As you can see here, the top of that Y is called the Fab region. This is the business end, and it's precisely shaped to bind to one specific enemy epitope. Once it latches on, it can just neutralize a virus or a toxin all by itself. But the bottom stalk, that's the FC region, the communicator. It acts like a beacon, signaling to other immune cells, hey, target acquired, come over here and destroy it. That process is called opsonization. It's basically like painting a giant target on the enemy.
And this factory doesn't just make one kind of missile, there's a whole arsenal. As you can see here, you've got IgM, that's the first responder, showing up in force to clump enemies together. IgG is the most abundant, it's the main warrior that gives us long-term protection, and it can even cross the placenta. IgA acts like a sentry, guarding the mucosal surfaces in your gut and airways. IgE is a real specialist, designed to fight parasites, but unfortunately it's also the main driver of our allergic reactions. And finally, there's IgD, which mostly helps get the B cell activated in the first place.
Okay, so the battle is won. The invaders are cleared out. But the adaptive immune system's most incredible feature isn't just winning the war, it's making sure it never has to be fought the same way again. And understanding this memory is also the key to seeing what happens when this powerful system turns against itself.
The first time your body meets a brand new pathogen, the response is actually pretty slow. It could take a week, maybe more, to identify the enemy, train the right T and B cells, and build up a big enough army. This is what we call the primary response, and it's during this lag time that we actually feel sick.
Now this graph is the whole story right here. On the left, you see that primary response after the first exposure. Notice that big time lag and the relatively small peak in antibody levels. That's you feeling sick. But just look at the secondary response on the right. When that same enemy comes back, the reaction is almost instant, and the antibody level is way, way higher, and it lasts longer. The army is already trained and waiting. This is immunological memory in action, and it's the fundamental reason why vaccines work.
So how do we get this incredible memory? Well, there are 4 main ways. There's natural active immunity, that's what you earn by actually getting sick and recovering. There's natural passive, which is where a baby gets antibodies from its mother. Then you have artificial active immunity, which is what vaccines give us. It's like training your army without having a real war. And finally, artificial passive, which is like getting a direct injection of pre-made antibodies for immediate but temporary protection.
So here's the crucial takeaway. During an infection, your body makes effector cells. These are the short-lived soldiers that fight the current battle. But at the same time, it creates memory cells, long-lived veterans of that specific war. But what happens if their training goes haywire and these veterans can no longer tell the difference between friend and foe? Well, this is autoimmunity. In diseases like multiple sclerosis or type 1 diabetes, our own defense force mistakenly attacks our own healthy tissues. It's just a tragic case of friendly fire, and it has devastating consequences.
And it's not just friendly fire. Sometimes the army just wildly overreacts to a completely harmless threat. This is called hypersensitivity. A type 1 reaction is your classic allergy, where those IgE antibodies we talked about go crazy over something like pollen. Other types can cause serious damage from immune complexes or even delayed reactions, like the one used for a TB test. So you see, this entire system is a double-edged sword. Its ability to learn, adapt, and remember is absolutely key to our survival, but its potential for error is also profound. So what does this delicate balance between defense and self-destruction really tell us about the intelligence of life itself?